completed the topic Rolle's law, and today our topic is colligative properties. Students, what do you mean by the colligative properties? Colligative properties of any solutions are those which depend only on number of the solute, but they do not depend on nature of the solute, are known as the colligative property. So colligative properties are those which depend only on the number of the solute particles. They do not depend what is the nature of the solute. Okay. There are mainly four types of the colligative properties: relative lowering in vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressures. These are the four colligative properties we will discuss. But today I will discuss only these two: relative lowering in vapor pressure and elevation in boiling point. Relative lowering in vapor pressure. Students, let us consider if we have a solvent, pure solvent in one container, that is A. This is solvent. If this solvent has the partial pressure, because it is volatile, so it will produce some vapor on the surface of the liquid, and these vapors will apply some force on the surface of this liquid. Let us consider this pressure is P0 A. This is the pressure of pure solvent. But student, if I add some solute particles, let us B is solute, and it is non-volatile in nature. It is non-volatile in nature. So let us consider if I add some solute particle in this. These are non-volatile. They are not producing the vapors, but they are lowering the vapor pressure of the solvent, because at surface some solute particles are also. Okay, so now partial pressure of the solvent is PA, and according to the Rolle's law, partial pressure of a component is directly proportional to the mole fraction of that. So here PA directly proportional to XA, and PA is equal to P0 A. Here P0 A is constant of proportionality, P0 A XA. So student, here before adding the solute, pressure of pure solvent is P0 A. But after adding the solute, here pressure is PA is equal to P0 A XA. Here PA is the pressure after adding the solute. So here change in pressure is P0 A minus PA, because pressure of the solution is lower as compared to the pressure of the solvent in pure state, because it lowers the particles of the solvent at the surface of the liquid. Okay. So now put the value of PA from equation 1. Here value of PA is P0 A X A. Now P0 A is common here, so take common it. Here 1 minus X A. Students, you know, total mole fraction of a solution is always 1. So here XA plus XB is equal to 1. So I can write in this way, XB is equal to 1 minus XA. Now put the value of 1 minus XA. It is equal to the XB. Okay, students. So I can write it in this way. Delta P. Delta P is equal to P naught A minus PA. So put the value of del P. P naught A minus PA. If I take this P naught A this side is equal to XB. So this is known as the relative lowering of the vapor pressure. And only this one. This is known as the lowering of the vapor pressure. Okay, student. It is a colligative property because with help of it, I can calculate the mass of the solute also. P naught A minus PA by P naught A is equal to XB. This is the equation for relative lowering of vapor pressure. Relative lowering in vapor pressure. Okay. So student, if I want to calculate value of the mole fraction, this XB is the mole fraction of solute. This is mole fraction of solute. Okay. You know very well. Mole fraction of a component, here component is B, is equal to number of moles of that component. Let us consider their number of moles of B are NB. Okay. Divided by total number of the mole. Student, here B is the solute and A is the solvent. Okay, let us consider total moles of the solute NB and total mole of solvent Na. Okay, so solute plus solvent, they form solution. Okay, so total number of the moles are Na plus Nb. But if we have weight only, so we can convert this mole into the weight, because we can calculate in this way. Number of mole is equal to given weight divided by the molecular weight. So let us consider given weight of the solute HWB and molecular weight of this is Mb. So put the value now Na. It is given weight of solvent by molecular weight of the solvent plus given weight of solute by molecular weight of the solute. But student, in dilute solution, Nb is negligible as compared to value of the Na. So we can neglect this one. Okay. So from here, Xb is equal to Wb by Mb divided by Wa by Ma. Okay. So it is equal to Wb by Mb into Ma by Wa. So this is the value of the XB. So put this value here. Put this value in this one. P naught A minus PA by P naught A relative lowering of vapor pressure is equal to, it is equal to XB, and value of XB we have calculated. It is this one. So WB by MB into MA by WA. From here, we can calculate mass of the solute because MB is the mass of the solute. Okay, so we can calculate from here. From here, MB is equal to, okay, we take it in this side, is equal to WB by, we will take relative lowering of pressure in opposite side, this into MA by WA. Okay, student. So by this we can calculate the molecular mass of the solute. So because it depends only on the number of the solute, so it is a colligative property. It is a colligative property. I hope it is clear to you. And our next colligative property is elevation in boiling point. Students, first of all, we should know about that. What is boiling point? Boiling point is the temperature. It is the temperature at which a liquid vapor pressure of a liquid becomes equal to atmospheric pressure. Becomes equal to the atmospheric pressure. Atmospheric pressure is the pressure of atmosphere. Okay, we take it 1 atmosphere, either 1.013 bars. Okay, so at which temperature vapor pressure of a liquid becomes equal to the atmospheric pressure, then that temperature is known as the boiling point. That temperature is known as the boiling point. Students, let us consider if we draw a graph. Vapor pressure versus temperature. Let us consider this is the atmospheric pressure. Okay, students, this is the atmospheric pressure. It is equal to either 1 atmosphere or 1.013 bars. And consider this is the vapor pressure of pure solvent. Student, if we will increase the temperature, then production of vapors increases. And if vapors increases, then they will exert more pressure. So vapor pressure is directly proportional to the temperature. Okay. So if temperature increases, then vapor pressure also increases. So let us consider at this point, pressure becomes equal to the atmospheric pressure. So this is the temperature where it becomes equal to the atmospheric pressure. So it is known as the boiling point because it is the boiling point of the pure solvent. So I can write in this way, TB naught. And you know very well, students, vapor pressure of the solution is always less than the vapor pressure of the pure solvent. And you have already seen in relative lowering in vapor pressure. So it will be lower as compared to the vapor pressure of the solvent. So let us consider it is the vapor pressure of the solution. Again, when we increase the temperature, vapor pressure increases. So let us consider at this temperature, at this pressure, it becomes equal to the atmospheric pressure, and at this, what is the temperature? So this is the temperature, and this is the temperature or boiling point for the solution. It is denoted by the TB. So you can see this is the boiling point of solvent, and this one is boiling point of the solution. So it is increases, and this is known as the, how much increase it is, this value, it is known as the elevation in boiling point, and it is represented by del TB. So from here del TB is equal to TB. TB is the boiling point of solution minus TB naught, boiling point of the solvent. So this is the elevation in boiling point. And students, elevation of boiling point is directly proportional to the molar concentration of a solution. Molar concentration means molarity. We take molar concentration because volume is not here, so it does not depend on the temperature. Okay. So students, elevation in boiling point is directly proportional to the molar concentration of the solution, and delta TB is equal to, now write the constant of proportionality, it is Kb into M. Here Kb is the constant of proportionality, or we can say Kb is the constant of elevation in boiling point. It is also known as the ebullioscopic constant. Sometimes name of this constant is asked to you. Okay, so you have to learn it. What is unit of this? Student, from here I can write it in this way. Kb is equal to del TB by M. And you know very well TB, this is temperature, and unit of SI unit of temperature is Kelvin. So Kelvin by molality. Molality, what do you mean by the molality? Number of moles dissolved in per kg of the solvent. In per kg of the solvent. This is the molality. Okay. So what will be the unit? Mole per kg. So from here, unit for Kb is Kelvin, kilogram per mole. And if our solution has molar concentration unity, if it has molar concentration 1, then from here del TB is equal to Kb. So what is the definition for the ebullioscopic constant? Kb is equal to the elevation in boiling point if molar concentration of a solution is unity. Okay, students. So from here, del TB is equal to Kb into M. We can calculate value of the mass of the solute also. You know very well, molality. It is the number of moles of solute, number of moles of the solute dissolved in per kg of solvent, per kg of solvent. Okay, let us consider if you have mass of solute. Okay, so you can convert given mass into the moles by this formula. Number of moles is equal to given mass by molecular mass. Okay, and if you have the amount of solvent in gram, so you can convert gram into the kilogram also by dividing it by 1000. So student, I can write it in this way. Del TB is equal to Kb into molality is given weight by molecular weight divided by per kg of solvent. If solvent is given in gram, so given weight of the Kb into, let us consider here solute is Xb, solute is B and solvent is A. So I can write in this way, given mass of solute by molecular mass of the solute divided by, if this amount is given in grams, so given mass of solvent divided by 1000. So from here we can write in this way, Kb into Wb by Mb into 1000 by Wa. Here Wb is the mass of the given mass of the solute and this is the molecular mass of the solute, and Wa, this is the given mass of the solvent. So this is the formula for elevation in the boiling point. From here we can calculate value of the mass of the solute also. How can we? Take Mb this side. So this is the molecular mass of the solute is equal to Kb, take del Tb in opposite side. Okay, so into Wb into 1000 by Wa. So by this formula we can calculate mass of the solute. Again, because it depends on number of the solute particles only, so it is also a colligative property. It does not depend on nature of solute. Okay students, so today we have discussed two colligative properties. First one is the relative lowering in vapor pressure and second one is elevation in boiling point. And I will explain depression in freezing point and osmotic pressure in next class. I hope it is clear to you. So thank you. Have a nice day.